Hey students, this is lesson 3-4. In this lesson, we are going to learn how to relate parallel and perpendicular lines. Let's go ahead and do the review here. I'll catch up with you. So an important property here in this lesson is the transitive property of parallel lines, theorem 3.8. Transitive property of parallel lines says if two lines are parallel to the same line, then they're parallel to each other. So if A is parallel to B and A is parallel to C, oh, that one makes sense, and B is parallel to C, then A is parallel to C. So the transitive features in there. And theorem 3.8, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So here we have two perpendiculars, and then we get two parallel lines. So I actually want a name for this instead of theorem 3.8. That doesn't work out very good for us to have that. So I think we're going to call this the two perpendiculars equals parallel theorem. All right, so let's go ahead and use those. This is just a quick little proof of theorem 3.8, and you can write it down if you want some more examples, but it's not in your packet. But so this is the theorem that says if you have two lines that are perpendicular to the same line, then the two lines are parallel. And so we're given, in this case, that R is perpendicular to T and S is perpendicular to T. Well, that means that the measure of the angles labeled here, 1 and 2, are both 90 by the definition of perpendicular lines. And then by the transitive property of equality, those two angles are equal to each other because they're both equal to 90. And then that means that they are congruent to each other by the definition of congruence. And then by the converse of the corresponding angles postulate, we get that the two lines are parallel. So, all right, we're going to go ahead and use that here to solve the problem. All right, I'm going to do a flow proof of this. And actually what we're going to show is that segment AB is parallel to segment CD, and it goes like this. So we know from the diagram that the measure of angle BCD plus the measure of angle DBC is equal to the measure of angle ABC. So I'm just showing that this plus this is equal to this. All right, and that is the angle addition postulate. Right now, from that we can just substitute, and we get, let's just put in the numbers for each of those. We get 68 plus 22 is equal to 90. Well, let's not put 90 in there. Let's put 68 plus 22 is equal to the measure of angle ABC. And then from that, we're going to just simplify. 90 is equal to the measure of angle ABC. And so this was substitution. And then the last one is just simplifying. And then, since we have a 90-degree angle, we can say that segment AB is perpendicular to segment BC, and that's by the definition of perpendicular. And by doing the exact same thing with these other angles here, with this angle, adding up to this angle, we get the exact same result. So I'm going to put those over here with 4 more boxes. And I'm just going to do that. Pause here. So essentially we have a duplicate of what we have on the left side on the right side. And now we can just bring those two results together and we get our conclusion using our new theorem, Theorem 3.8, and that if we have two things perpendicular to the same thing, then the two lines are parallel. So right here we get AB is parallel to CD, and that's Theorem 3.8, but we're going to call that two perpendiculars is equal to a parallel theorem. All right, I'm going to let you try one. All right, another theorem we're going to use is a perpendicular transversal theorem. In a plane, if a line is perpendicular to one of two parallel lines, and it's also perpendicular to the other. So the idea here is that if both of these, if this line is perpendicular to one parallel line, then it is also perpendicular to the other. So if A is parallel to G and A is perpendicular to T, then A is perpendicular to G. I said that wrong. A is, G is perpendicular to T. There you go. So if C is perpendicular to N and N is parallel to P, C is perpendicular to P. That's the idea there. Okay, we're going to use some of these ideas to prove this. We're going to do the first part and the second part. So we're going to prove that C is parallel to D, and in the second part we're going to prove that A is parallel to B, but you're going to do that in the Got It. So we're going to do a flow proof here again. Let me put up some rectangles. All right, so the first thing we're going to do is try and prove that C is parallel to D. So that's what our result is going to be. We'll give that reason for that in a second. But we know that C is perpendicular to B. And we also know that B is perpendicular to D. And so, and those are givens, so we can just write given for both of those. Then by our two perpendiculars equals parallel theorem, we can say that C is parallel to D. That's an immediate result because we have C is perpendicular to B, B is perpendicular to D. So that means that C must be parallel to D, and that's by the two perpendiculars equals parallel theorem. All right, go ahead and try the Got It here. And I hope you realize that I'm using that symbol to represent parallels there. All right, go ahead and do the lesson check and be ready to share that with us in class the next time we meet.